We've defined Legendre symbols, which is a way to represent what numbers are or are not quadratic residues modulo p, and now we're going to learn our first approach to actually compute them. So here's the general problem. We just want to solve the following question. Compute the value of the Legendre symbol n over p, where p is an odd prime. When p is relatively small, we can do it just by brute force. For example, compute the value of the Legendre symbol 10 over 13. 13 is an odd prime, so we square the first half of the standard complete residue system mod 13 to see if 10 shows up or if it doesn't. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Ah, look, 6 squared is equivalent to 10 modulo 13. So 10 is a quadratic residue mod 13, so the Legendre symbol has value 1. Now, as another example, given that 1217 is prime, compute the value of the Legendre symbol 651 over 1217. In theory, we compute the squares of the first half of the complete residue system mod 1217 and check if 651 comes out or if it doesn't. Now you might get really lucky. A relatively small value might square to be 651, but you might get unlucky. It might be something like 598 squared is equivalent to 651. I'm just guessing. I don't know if that's true or not. In which case you'd have to go very deep into the list before you found an answer, or maybe you'd have to go all the way through this list before determining, well, it never showed up, therefore it's not a quadratic residue. So once the base gets relatively large, this brute force method becomes a bit too slow. So we're going to start developing faster techniques to determine which numbers are or are not quadratic residues mod p. The first thing we want to do is establish Wilson's theorem. We could have proved this a while ago, but it never really came up. For any prime p, p minus 1 factorial is equivalent to negative 1 modulo p. If p is 2, then I just get 1 factorial, which is 1, but modulo 2, 1 is equivalent to negative 1. So if p is 2, the result is true. Now let's assume that I have a prime p that isn't 2, in other words, an odd prime. Now p minus 1 factorial is just the product of 1 through p minus 1. In other words, it's a product of the standard reduced residue system mod p. Since every element of a reduced residue system is relatively prime to p, they all have inverses modulo p. So if x is equivalent to x inverse, okay, let's assume I have something, it has an inverse, but its inverse is itself. Well, if I multiply both sides by x, I get x times x, that's x squared, and x times x inverse is 1. So anything that is its own inverse will also solve x squared equivalent to 1 mod p. The definition of this is that p is a factor of x squared minus 1, which factors thusly. Since p is a prime, if it's a factor of a product, it's a factor of one of the two things. Now, if p is a factor of x plus 1, then x must be equivalent to negative 1 mod p. While if p is a factor of x minus 1, then x must be equivalent to 1 modulo p. So we started with x is its own inverse, and we concluded with x is either 1 or negative 1. So the only elements of a reduced residue system that are their own inverses are 1 and negative 1. So when I compute p minus 1 factorial, I multiply all the elements of the reduced residue system mod p. I make pairs. Okay, if something has an inverse that is different from itself, I pair them off with each other. Everything can be paired off in this way except for things that are their own inverse, but the only things that are their own inverse are 1 and negative 1. So p minus 1 factorial is just the product of 1 through p minus 1. Note that modulo p, this last number is equivalent to negative 1. So in the interior, things have inverses, and I pair them off to produce a bunch of 1s. 1 has an inverse, but it's not different from itself. So it doesn't get paired off with anything, but it's already just 1. Negative 1 is its own inverse, so it doesn't get paired off with anything different, so it has to remain there. So 1 and negative 1 did not get paired off with their inverses because they are their own inverse. Everything else in the middle has an inverse which is different from itself, and I pair those up to get a bunch of 1s. So p minus 1 factorial is ultimately just negative 1 modulo p. It's an interesting thing to remark that the proof is different when p is 2 versus an odd prime. We've already seen that odd primes are somehow nicer than 2. for a lot of statements in number theory. What this boils down to 9 times out of 10 is that modulo 2, 1 and -1 are equivalent, but modulo anything else, they are not. So 1 being the same thing as -1 can cause some unexpected things to happen. So primes are nice for their own reasons, but if you don't want 1 to be the same thing as -1, then you don't want to consider 2. So here's how you end up with a lot of statements about odd primes where you have to throw out 2. So here's our first theorem in computing the value of Legendre symbols. It's due to Euler. We'll be referring to it as Euler's method to slightly distinguish it from other things we call Euler's theorem. Suppose P is an odd prime and A is relatively prime to that. Then the Legendre symbol A over P may be computed as A to the phi of P over 2 modulo P. To prove this, begin with the standard reduced residue system mod P, so just the list of integers from 1 to P minus 1. We're going to create a function f that maps this list to itself. So for everything in the list x, we're going to pair it with something y. The procedure is a case-wise procedure, however. So pick a value x in the list 1 through P minus 1. If x squared happens to be equivalent to a modulo P, then I assign the value of y to be negative x mod P. Under this assumption, y squared is negative x squared, but negative x squared is the same thing as x squared, and x squared was assumed to be a. So if x squared is equivalent to a, then f of x, which is y, also has square equivalent to a. And since p is odd, x is not the same thing as negative x modulo p. In other words, x is not the same thing as y. So I have in fact made a distinct pairing. X gets paired off with y, which is a different thing. And what's their product? Okay, I know x squared is equivalent to a, and I know y squared is equivalent to a, but what's x times y? Well, y was taken to be negative x, in which case the negative sign factors out and I get negative a. So if x was chosen and it happened to have a square equivalent to a, then I define f of x, aka y, to simply be negative x. This is a different element from x that I started with, and the product x times y will be equivalent to negative a. So whenever I pick something whose square is equivalent to a, the function says pair this off with the other thing whose square is a, and then the product of those two elements will be negative a. Now let's suppose you picked an x whose square wasn't equivalent to a modulo p. Since we are in a reduced residue system mod p, we are relatively prime to p, so there is some x inverse, in which case I give y the value ax inverse. Now if I do x times y, since y is ax inverse, these inverses cancel, and x times y is equivalent to a. So when x squared was equivalent to a, x times its associated value f of x will be equivalent to negative a. When x squared isn't equivalent to a, x times f of x will be equivalent to a, not to negative a. Also, let's suppose x and y are equivalent. If I multiply both sides by x, over here I'll get x squared, and here the x and x inverse cancel, leaving behind just a. However, we assumed x squared wasn't equivalent to a. So therefore, this can't happen. X can't be equivalent to y. So under both cases, we map x to a value y, which is different from itself. X and y are never equivalent. If x squared was equivalent to a, then x times its buddy is equivalent to negative a. If x squared was not equivalent to a, then x times its buddy is equivalent to a. So we always match things up with every x gets matched with a y. That is not the same thing. If the x I started with squares to be a, then xy will be equivalent to minus a. But if x squared wasn't equivalent to a, then I pair it off with something so that xy is equivalent to a. So let's continue this proof. What we do know, if p is an odd prime and a is a quadratic residue, then there is a solution x squared equivalent to a mod p. But since p is an odd prime, we actually know there are only two solutions, the x that we found and negative x. But remember, under our function, these two things are paired off with each other. So if a is a quadratic residue mod p, then the previous pairing we described will produce exactly one pair that multiplies to negative a. Whenever there is a solution x squared equivalent to a, we paired off x with a value y and saw that x times y was equivalent to negative a. But that can only happen once. Otherwise, all the other pairings will simply produce an a. So when I multiply the entire reduced residue system together, there's one, under the assumption that a is a quadratic residue, there is one pairing of x with negative x, whose product gives me a negative a. All the other pairings just give me a's over and over again. On the left, I just have p minus 1 factorial, and on the right, I'm just going to factor the negative sign out to get a bunch of a's in here. By Wilson's theorem, this is equivalent to negative 1 mod p. Now on the right, I have a bunch of a's. How many? I get one factor of a for every pairing I accomplished. There were p minus 1 elements in the reduced residue system mod p, so how many pairs are there? P minus 1 over 2, half as many. So on the left, I get negative 1, and on the right, I get negative a to the p minus 1 over 2. So, in other words, the Legendre symbol a over p is equal to 1 because we assumed a is a quadratic residue mod p. And by canceling a negative 1 here, 1 is equivalent to a to the phi of p over 2, meaning these two things are equivalent modulo p under the assumption that a is a quadratic residue mod p. Now we can wrap up the proof. What happens if a isn't a quadratic residue, aka a quadratic non-residue? Well, then the Legendre symbol would have to take value minus 1. But since I was never able to find an x squared equivalent to a modulo p, I never produced a pairing that made a minus a. The only pairings I make a's. So if I multiply all elements of the reduced residue system on the left, they pair off to just produce a over and over again. Now each a here corresponds to a pairing in the left. So the left is negative 1 by Wilson's theorem, but the right simply has one factor of a for each pair. There were p minus 1 elements over here, so there are half as many pairs. So I simply get negative 1 is equivalent to a to the p minus 1 over 2 mod p. But we do now get our desired result. Since we assumed here a is a quadratic non-residue, this Legendre symbol is minus 1, and minus 1 is equivalent to a to the p minus 1 over 2, and p minus 1 is, of course, phi of p. So in either case, we got this result. Either this is 1 and this is equivalent to 1 mod p, or this is minus 1 and this is equivalent to minus 1 mod p. So let's work through an example. Negative 1 is a quadratic residue mod p if and only if p is equivalent to 1 mod 4. So first, if p is odd, then it's either equivalent to 1 mod 4 or to 3 mod 4. Suppose p is an odd prime and p is equivalent to 1 mod 4. Then p is a multiple of 4 plus 1. So phi of p is p minus 1, which is just going to be 4k, in which case phi of p over 2 is just 2k, some even number. When p is equivalent to 1 modulo 4, then phi of p over 2 is even. But if I apply Euler's method, we get the Legendre symbol negative 1 by p is equivalent to negative 1 to the phi of p over 2. Under the assumption p was equivalent to 1 mod 4, this exponent is even, and negative 1 to an even power is just 1. So, under the assumption that p is equivalent to 1 mod 4, this Legendre symbol evaluates to 1. In other words, negative 1 is definitely a quadratic residue modulo p. So, when p is equivalent to 1 mod 4, negative 1 is a quadratic residue. On the other hand, if p is equivalent to 3 mod 4, well then, p would be equal to 4k plus 3. Phi of p would be p minus 1, which would be 4k plus 2. So phi of p over 2 would just be 2k plus 1. So when p is equivalent to 3 mod 4, phi of p over 2 is odd, in which case, applying the same reasoning gives me negative 1 to an odd power, and negative 1 to an odd power is negative 1. In other words, the Legendre symbol negative 1 over p is negative 1, which means negative 1 is a quadratic non-residue, modulo p. So Euler's method has allowed us to quickly tell, is negative 1 a quadratic residue, modulo p, yes or no, without having to go through the brute force of actually squaring things. We have proven -1 is a quadratic residue modulo p if and only if p is equivalent to 1 mod 4. Now there are some impracticalities regarding Euler's method. It turned out to be very convenient to check whether -1 is a quadratic residue mod p or not. But for other values, it would be very unpleasant. Earlier we asked, is 651 a quadratic residue modulo 1217 or not? It's not especially practical to compute 651 to the 608th power modulo 1217. The successive squaring algorithm helps. It's probably more work, to be honest, to do the successive squaring algorithm than to do brute force. If you're working by hand, you probably just want to brute force this at this point. We're going to learn better ways to do it, however. So Euler's formula might also tell us, even if we can do it, whether the Legendre symbol is equal to 1 or -1. In the first case, it tells you there is some solution to x squared equivalent to a modulo p, but it doesn't actually tell you what the solution is. So even if you know that a number is a quadratic residue mod p, it doesn't actually solve x squared equivalent to a mod p. It doesn't tell you what number squared is equivalent to a. It just tells you a solution exists. For example, 1217 is an odd prime, and it's actually equivalent to 1 modulo 4, which means -1 is a quadratic residue modulo 1217. So there is some x, so that x squared is equivalent to -1 modulo 1217. But we really don't have a lot of information on how to find that solution, only that it exists. Now I'll mention as an aside, when the base is equivalent to 1 modulo 4, there is actually a way to solve for what square is equivalent to your desired value. But we're not introducing it here. What we are going to do, however, in further videos is develop more efficient tools for computing the Legendre symbol A over P. Our end result is something called the law of quadratic reciprocity, which really simplifies things. These techniques do help you determine whether A is a quadratic residue mod P, but they don't actually help solve what squared is equivalent to A mod P. So that notion we kind of set aside. We're generally not going to be concerned with solving this, just asking, is there a solution at all? In other words, computing the value of these Legendre symbols.